Hello, good morning, good afternoon, good evening, depends on when you're watching this. I'm Hector, and today we'll be doing the OER, the Open Educational Resource presentation, and I am a chemistry major, so I will be showing you something from my chemistry field, from what I do, something that we use every day, almost every day, and that'll be the periodic table. With the periodic table, we basically use it to do anything and pretty much everything. We use it to balance our reactions. We use it to calculate reactions to see what substances we get. Basically, almost everything we do involves a periodic table because chemistry involves the elements and the elements do the chemistry part. So yeah. We'll be looking at the four basic things that you can see in a periodic table. You can call them trends, orders. They're basically what those are. And the four are how the little squares where each element is, how those look, and then the numbers on the top and on the sides of the periodic table, what those show and what they represent. And then we will be looking at one of the basic trends that you can see on the periodic table when reading it. So the first thing that we will be looking into is the design of each individual element. So I took the liberty to do fluorine for you. It's just a basic element. Each element square is split up into between four basic parts: the atomic number, right here, the symbol, the name of the element, and the atomic weight of the element. The atomic number is above the symbol on either the left, top right, or top center. Either or depends on which periodic table you look at. They can have it wherever they feel like it, but it's usually up there. This tells you the number of protons an element can have, the number of electrons the element has, and it tells you where in the periodic table this element lies. It is, in this case, fluorine has 9 electrons and it has 9 protons, so there's fluorine. And then the symbol, it is the letter that represents that element. In this case, F for fluorine, and the letter that can usually come from its the name's origins. It can come from Greek, it can come from Latin, or even German. And F just represents fluorine, but usually the symbols don't always align with the name of the element. For instance, silver. The symbol for silver is Ag, which has nothing to do with silver, and also a tin. The symbol for tin is Sn. So they don't always align, but those symbols are there to represent that element. And then you have the name of the element, of course, which can be derived from, again, German, Greek, Latin. And it tells you just the name of the element, but in some cases they can tell you more about the element. In the case of hydrogen, they can tell you when you burn hydrogen, it combines with oxygen to form water. Therefore, the Greeks called it hydro. And hydrogen, gen for generates water. Hydrogen, that's why they called it hydrogen, because when you burn hydrogen, you get water. So that's basically it. And then you have the atomic weight. The atomic weight is at the very bottom of the little individual square, and it can tell you the mass of the element itself. And we basically use that mass for learning how to balance our equations, to do calculations for reactions, so we end up with the same amount of stuff on each side, things like that. Another trend we will be looking at is the numbers on the top of the periodic table and on the left hand side of the periodic table. So as you can see on the top, there are a series of numbers that go from left to right, 1 through 18, and then on the left there are a series of numbers 1 through 7. They go top to bottom, 1 through 7 again, and these help you understand the periodic table better. When looking at the numbers 1 through 18, they first tell you the column that it's on, because the periodic table is split up between columns, which are these, and rows or periods, which are these. And basically the numbers are there to tell you which column, but then there's also a second-hand thing when looking at the periodic table to try to learn how many valence electrons an atom has. A valence electron is the the number of atoms that are in the last shell of the atom. Atoms are split up and they have shells, some more than others, and however many electrons are in that last shell is represented by these numbers. So with this column you can see 1, so all of these elements only have one valence electron, one electron in their last shell, and 2, these elements have 2 valence electrons. And then over here starts getting more complicated. With the transition metals, they can have any number of valence electrons. They're very different. They have many numbers of valence electrons. They can vary drastically. But here, they pick us up again. So with 13, 14, 15, 16, 17, and 18, you should typically subtract 10 from those. So this would be 3, 4, 5, 6, 7, 8. So you can continue 1, 2, 3, 4, 5, 6, 7, 8. These have 3 valence electrons. These have 4 valence electrons, 5 valence electrons, 6, 7, and 8. 8 valence electrons means that the shell is complete, it is stable, and it is happy being there. It is non-reactive. So yeah, the less valence electrons you have, the more reactive an element is. The more valence electrons you have, the less reactive it is. So less electrons, more reactive. More electrons, less reactive. So that's one easy way to tell. And then that's with these. And then with the numbers along the side, the 1 through 7, they tell you how many shells each element has. So, and like I said, the shells are like the layers of electrons in each atom. So in hydrogen and with helium, you only have 1 valence shell, and this one only has 1 valence shell with 1 valence electron, and this one has 1 valence shell with 2 valence electrons, and so forth. That's how it goes. The first shell can only hold 2, so that's why there's not 8 valence electrons here, and because in the first shell it can only hold 2 valence electrons, and then so forth with these. With lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, there are 2 valence electrons in that second shell. They have a second shell, and they have a second shell, and they have their varying valence electrons, and so forth. Third shell, they have 3 shells, they have 4 shells, 5 shells, 6 shells, 7 shells. So these numbers tell you how many shells are in that atom. And then the last trend we will be looking at is the atomic radius trend. This one's a little more difficult to understand, but it's pretty easy. It's difficult and easy at the same time. It's weird. So when looking at the radius of an electron, you gotta look at how big, like how wide it is from end to end. That's your electron. No, not electron, atom. That's your atom. How big it is. So when looking at the trends, this shows the trend of atomic radius. Let me show you this one. This is easier because it's blank. So each atom has its number of electrons and its number of shells. So the way the trend goes is the further down you go, the bigger atomic radius you get because you're adding shells. So lithium has 1 more shell than hydrogen, so lithium is larger than hydrogen because it has 1 more shell. But the more right you go this way, the smaller your radius gets. Let me explain. With lithium again, you have 2 shells, 2 electrons in the first shell, 1 electron in the second shell, and then you have beryllium. It has 2 electrons in the first shell, 2 electrons in the second shell. But since you have 1 extra electron, your shell shrinks, your atom shrinks because you're adding more electrons, which means there's more attraction between the protons and the electrons in the atom, which brings everything closer together. So the more valence electrons you have, the tighter your element or your atom is, because you have more electrons pulling and on those protons. So the trend is the further down you go, the larger your atom gets because you're adding more shells, but the more right you go, the smaller your atom gets because you're adding more valence electrons, which continues to add to that pull and pressure. So this adds to this trend, the southeast facing arrow. which means the more down you go, the bigger they get, but yet the more right you go, the smaller they get. And that goes for all the elements in the main series. And here's another description about it. You have the carbon atom, which has the 4 valence electrons, and it's happy right there. But then you have the nitrogen atom, which has the 5 valence electrons. They have the same amount of shells, but since this one has 1 more electron, there is more pull on that other proton inside of this atom, which makes it smaller than the carbon. As you can see, it's slightly smaller. And then that's as you go towards the right. But as you go down, you have neon, carbon, and nitrogen right here. So as you go right, they get smaller. And then neon is right here, right there. And then sodium is right here. So sodium has 1 more shell added to it. And since it has 1 more shell, it gets bigger because you have that extra shell now to make it larger. It's still slightly tighter, but it's still larger because you added that other shell to it. So again, the more down you go, the larger they get, but the more right you go, the smaller they get. So that's basically it. And these are the 4 trends that are easy to remember, that are good to know when studying chemistry, because they help you tremendously when trying to do basic chemistry in the sense. So I hope this was informative, and that's my presentation. Goodbye.